Lesson 2, identifying vectors. Also, if you can't see the PowerPoint, let me know. Because obviously, yeah. This is what I want you to write down. We will learn about some of the ways to write down vectors. So there are actually, pardon me, there are actually multiple ways, but yeah. Okay. So I've got my pen. Let's start. So last time in class what we did was we talked about what an engineer does, what an engineer is, and my expectations of you guys, how we're going to run the class, so on and so forth. After we did that, we talked about the engineering process. We talked about what an engineer does. Again, I showed you a video for that. And then we did the engineering process. So what is the process that we use? And therefore, I was using that as a bit of a heads up. Guess what? We're going to be doing this similar sort of process later on. We're also going to be looking at the other process as well, that an engineer says what problem needs to be solved and who is it important for. That's something we're going to be talking about later as well. We wrapped up by talking about vectors. We said a vector is a line or a measurement that has a direction. So you can say 2 meters north or 10 newtons up, whatever it is. Whereas a scalar just has a direction but no size. And then we finished up by talking about how we can symbolize vectors. We said a vector can either be symbolized with a bold letter, letters in with arrows over them, like A or X, Y, whatever, or with a tilde under it, like this, like J. Lengths are always positive, and you can measure the size of something with a straight line. And the last but not least, we said that equivalent vectors have the same magnitude and the same direction. What's interesting for that is these two here and this one are all equivalent vectors because they're all the same length and they're all going in the same direction. But they don't have to start at the same point. That's going to be part of today's lesson. So, identifying vectors. Let's actually, before we move on, let's link vectors to what kind of maths that we're going to be linked to it. And this is actually going to be useful. So the type of maths that we're going to talk about when we talk about vectors, we're actually going to talk about 3 types of maths that you guys are familiar with already. The first type is going to be linear graphs. Now, linear graphs are really useful for vectors because what linear graphs allow us to do is they allow us to plot vectors in 2-dimensional space. So therefore, being able to say, oh, it's this and this and stuff like that is really important. After linear graphs, the next important one to talk about is going to be trigonometry. If I've got a vector that's going up like this, I need to be able to figure out what is this angle here. So I'm going to need to, because I need to be able to give a direction. I can't give a direction if I don't know what the angle is. So that's something we're going to be looking at too. That's another part of year 9 science that you're going to need to have. The third one is going to be this. The size of a vector can be found using Pythagoras. So we're actually going to use each of these three things, and we're actually going to spend the next week talking about how each of these three things interlink. We're going to be mostly focusing on this one today, but in the next coming lessons, we're going to be talking about trigonometry and Pythagoras as well. So get ready, because you will be seeing a fair few of these things. So let's start with defining vectors. What I'm going to ask you to do, and I'm actually going to give you guys about 2 minutes to do this, is what I'd like you to do is on a spare piece of paper, or if you're trying to do this electronically, you're going to struggle. But what I would like you to do is I'd like you to draw the Cartesian plane on the left. I'd like you to put this into your books. Draw it or sketch it or something. I'll give you 2 minutes. Make it fairly big, because we're going to be drawing on this as well. And also, I'm going to be reusing this same axis later on, so that you can afford to make it big, maybe 10 centimeters by 10 centimeters, that's fine. Question? Someone's asked if I can put the lessons online. The answer is yes, I can. I haven't put them online yet, just because I haven't had time, but I will put them online soon. But you should still find something that you can jot this down on, even if you don't have an exercise book. As I said, just putting this down on paper or something you can transfer over later on, even if it's just white printer paper. You can get an exercise book later on, but yeah, and I'm going to put these slides all available on the classroom so that you can open them up. And what I'm also going to do is I'm going to get them to the point where you can follow along with the lessons as we go. So that's going to be the next sort of part. But all I had time to do today was just to get the homework task online. And I thought that was really important, because I want to give you guys a chance to work on that homework task. So what we're going to do is we're going to define some vectors. In order to do this definition, I've already created 3 points. Point O, which is going to represent the origin, point A, and point B. And we're going to use each of those points to draw some vectors. The first thing we're going to draw is we're going to draw in vector OA. Now, vector OA, in this case, is the vector that connects point O to point A. Let's draw that in. Now notice how I've also drawn an arrow here. That's because, yeah, the direction that we're going is important. That's vector OA. Yep. Good. That's it. And because, yeah, it's just the vector that connects point O to point A. Now let's do some other vectors. Let's do vector AB. Let's do that in a different color. Let's go with orange. Vector AB is going to look like this. And it's the vector that connects A to B. Quite simple at the moment. But, you know, like, we're going to have some simple problems. That's fine. Let's do vector AO. Now, vector AO is not the same as vector OA. Vector AO is actually in the opposite direction. We say vector AO is actually this way. And it's going to be difficult to draw, because I've already drawn a line there for OA, but still. An interesting fact is something I'm going to draw here. Vector AO is actually equal to vector OA, but the difference is that this is going in the opposite direction. So because this is going in the opposite direction, it's actually not equal to OA, it's equal to the negative of OA. Negative is like the anti. So AO is like, say, the anti-OA. If you think about it, if you followed OA and then you followed AO, that's like canceling it out. That's why we say it's like a negative. And so you end up at 0. So you may want to write this fact here down as well. Now we're going to do one more interesting point. This last one is designed to kind of, I don't know, rock your world a little bit. We're going to draw vector OA from point B. Now, what does vector OA look like from point B? Vector OA from point B looks like this. This is where some students start to get a little bit confused. Like what, how did you do that? Remember, a vector is a size and a direction, okay? In this case, vector OA is 2 units along the diagonal. And I can draw that from any point. I don't have to do OA between O and A. For example, I could do OA here. There's vector OA. Here's another vector OA. Because each of these is going 2 units, or well, you know, up in along the diagonal, up and to the right. That's what makes these vectors, that's what makes vectors powerful, is that they're just the direction and the size. You don't actually have to need to know, it can be from any point. The example that I usually give for this, is the, and this only works if you've actually played chess. If you haven't played chess, it's not helpful. But for me, the example that I usually give for this is the horse in chess. So the whole point of the horse in chess is it can move 2 spaces up and 1 space to the right. And the advantage of that piece is it can actually repeat that move anywhere it wants on the whole chessboard. It doesn't just have to repeat it in the same spot. So it can actually do it from here, from here, from here, anywhere you want. Same way that you can follow vector OA from anywhere you want. And also I'm aware, for those of you that are chessmen, there are other ways you can draw this in. Okay, I'm going to open this up at the moment. We're not going to open it up. I'm going to quickly check chat. Is there any questions here? Any confusions? Anyone lost? Are we all good with so far with vectors? Yeah, okay, thanks, Evans. If anyone's really confused, you need to say so, either in chat, send me an email, whatever. But at the moment, I'm going to assume that we're all pretty good, so I'm going to keep pushing through. I'm going to show you guys. I'm going to change the slide here, and I'm going to get you guys to write down IJ notation. But I want you to do these little squiggles underneath IJ notation. This is a different way. This is a very first way of writing down a vector. Because obviously you can't just write OA and AB, because if I don't know where O is and I don't know where A is, you can't do that. So what's a good way that we could write down a vector? So IJ notation, what does that look like? What does it do? Let's take the vector 2 right and 2 up. Okay, 2 right and 2 up. So that would look like 2 to the right, 1, 2, and then 2 up, 1, 2. So it's the vector that connects these 2 points. Actually, that's the same as OA, but now we've actually given it a name. So here, if we look at OA, we go 2 to the right and then 2 up. So that's just a different way we can refer to it. If we start at the origin, what would it look like? Well, it would look like this. 2 to the right, and 2 up, gets me this point here. That's what the vector O, that was the vector 2 to the right and 2 up. That's what it would look like. Mathematicians have a way of writing 2 to the right and 2 up using the letters I and J. Now, this notation is just a very special kind of way that we can write it. What they do is I is 1 unit to the right. It's like X. So if I say 3i, that means I'm going 3 units to the right. If I say 4i, it means I'm going 4 units to the right. If I say negative 2i, where do you think that's going to go? Where do you guys guess? Write it in the chat. Or you can say it out loud if you want to unmute yourself. Where do you think negative 2i is going to go? Someone has guessed. David. Bottom left, close. If two left on the x-axis, yeah, just left. So David, you were close. It is left. It's not bottom left. It's just straight left. So 2 units to the 2i would be 2 units to the right. Negative 2i would be 2 units to the left. Guess what j is? J is 2 units up. And J is like Y. I like to sometimes, if I get confused, I think J for jump. So J is up and down. It's jumping up and down. And so that means we can actually write 2 right and 2 up using this notation. What would it look like? It would look like this. M, that's just a random name for this vector, vector M. It doesn't matter. Is 2i plus 2j. Because it's 2 to the right and it's 2 up. Now, this is going to be a bit difficult for some people, but ultimately you just need to remember that I is exactly the same as X. I just means left and right. J means up and down. I'm going to move on, unless someone yells out, stop, please, sir, you're going too quickly. And you guys can do that. You can even message me privately and say, sir, can you slow down? And I'll slow down. No one has to know that you asked me. Some of the advantages of the private chat function. That's okay. We're going to jump to the next slide. We're going to look at this 2i plus 2j. We're going to follow that from point S and point T. Can I get you guys to add point S and point T to your Cartesian graph that you drew before? All right, let's follow 2i plus 2j from point S. That's going to be 2 to the right and then 2 up. So we're going to finish here. So the vector will look like this. Whereas if we follow it from T, 2 to the right and 2 up, it's going to be here. It's going to look like this. T is going to end up 3, negative 2. Whereas S is going to end up at negative 2, negative 3. Not that it's too important, but that's sort of what the question asks. So I thought I'd better do it. What else is on this slide? Oh, that's it. So that's just there. There's just a little bit more examples at IJ notation. Now there's a lot more we can do with IJ notation. Remember, IJ notation is just how much left and how much up. What we're actually doing is we're breaking vectors down into smaller parts. We're breaking them down into their left and right parts and their up and down parts. So let's now look at what happens if we have a different scenario. I'm going to change the slide. We all copied it down. We're all good? Okay. We're going to now do this. What is the vector connecting the origin to point 4, 5? This is going to be, we're going to now explore how we can get IJ components from just points. So let's just say we've got the vector, the origin. Can someone tell me what is the coordinates for the origin? Zero, zero. Thank you both, Dylan and Elaine, who sent that through. 0, 0 is the coordinates of the origin. And so we're going from 0, 0 to point 4, 5. Does someone want to take a guess? Let's call this vector vector A. Can someone tell me how far to the right have we gone if we go from 0, 0 to 4, 5? How far to the right have we traveled? 4. So I can actually write this down as 4. And which letter has got to do with left and right? I. Yeah. Thank you, Dylan. 4I. And how far up has it gone? 5. And what symbol do you think I should use for that? 5J. Beautiful. Plus 5J. Nice and easy here. Now, the vector connecting negative 2, 3 to 4, 1, what will that look like? Well, let's have a look. You could say, well, how much have I gone from if I go from negative 2, 3 over to 4, 1. There's a couple of ways you can do this, but we could actually just use this, right? We could actually just say, well, let's figure out the run. Let's go x2 minus x1, or 4 minus 2. Equals 4 plus 2, which is 6. If I go from negative 2 to 4, I've moved across 6. So that means that this one's going to be, for B, we're going to have the first part of B, is going to be 6I. Now, for the rise, we would just do y2 minus y1, which is going to be 1 minus 3. Now, 1 minus 3 is going to give you a negative number. It's going to be negative 2. So that means we're going to have a minus 2j. And that's our vector for connecting those 2 points. Are there any confusion here? Is anyone confused or scared or nervous about what the heck's going on here? I'm actually going to show you one more trick with this. Is it on here? Oh, it's not on here. So I'm just going to show you that trick here. It's something a bit new, so let me know. But we're going to do this. I wonder if I can just quickly, pardon me. I'm actually making a brand new slide. This is an old PowerPoint. I haven't actually added new slides in a while. Give me a sec. So I can actually show you guys. Let's do this one. I'm actually just going to write it down, so you just have to. We're going to follow where does the vector C equals negative 3i plus 7j terminate? Yeah, I like terminate. If it starts at, we'll go with -2, -2. You could say end, where does it finish? But I like this one. We're going to go with this. Just as something, because I think this pops up a couple of times in the worksheet that I'm going to give you probably tomorrow. So I thought it might be important for me to go through it here now. Where does the vector C, -3i plus 7j terminate if it starts at -2, 2? -2, -2. Well, some people have already started guessing. Let's find out. Well, we know that it's going to, that the -3 is going to be our, we know that the -3 here is going to be our, where is it? Where's my blue one? This is going to be our run. So therefore, if I've got -2, I go, well, I'm going to take this -2 in the x, I'm going to minus 3, which is going to be -5, is going to be my x variable. Whereas with the y variable, we've got -2, but this time we're going to be adding 7. So that's how we're going to change it. We're going to add 7. So this one was, that one was adding -3. So if I add 7 to this, I get -2 plus 7 happens to be 5. So where does this end up? This, after following this vector, we end up at -5, 5. Now this is exactly the same thing that we did here. The only difference is that in this one, when we drew it, we had to go, okay, cool. But now I can just give you any old coordinate and you guys can follow it to where it ends up. So that's how we can follow a vector. So I want to do that. No, I don't want to do that. I'm just trying to figure out if I should teach you guys this last bit. There's only 4 minutes left in the class. So what I think I might do is I might leave it there. Did I make a mistake, guys? Oh, hold on. No, I think I got it right. Someone's like saying that I made a mistake, but I don't think I made a mistake. 1,5 is what someone's suggesting. Let me just double check here. -2 minus 3 is going to be -5. -2 plus 7, that's going to be 5. Yeah, okay, just double checking. Okay, cool. I'm going to leave this here. So this has been the lesson so far today. Recapping it just quickly, what we did is we talked about how vectors can be linked 2 points to one another. I said one way we can describe vectors is with IJ notation, where I is to the right and J is up and down. Once we just learn that as a way to describe vectors, we then started to follow some vectors from different points and figure out what the vectors would be from those 2 points in IJ notation. And then we practice following a vector from just any old vector using 2 coordinates. What we're going to do next time is we're going to deal with the same thing we do with math all the time: adding, subtracting, and multiplying back vectors. That should bring us to the end of this vectors, the first thing. So that's what we're going to do next time.